All right, this is more or less the last time I'm going to talk about Fourier series. I'll talk about probably a little tiny bit at the beginning of class, but I'll start talking about something different on Wednesday called Fourier transforms, which are closely related. All right. And seriously, don't be on Discord in the middle of class. All right. You guys were sending me emails and Discord stuff in the middle of class last time. Don't be doing that. All right. Obviously, that's the worst time to be doing it. All right. So I'll continue, I guess, with the Fourier stuff. So again, there's really only two sections on Fourier series. This is 9.1 and 9.2. That's all we need. I don't know. That is all right. So to wrap up, last time we started talking about the ways that we could identify the coefficients kind of in a more general sense. So whole idea with Fourier series, again, just to circle back on the big concept of it, is if I gave you something like a circuit or some kind of a system, doesn't have to be a circuit, but in general, it could be any kind of dynamic system. If I want to figure out if I put a waveform, let's say Vn, into this system, and I want to figure out what's the response at, let's say, to V out, or what are the currents and voltages throughout that circuit, then what I have to do is write a differential equation. All right, what you learned in 2112 is that I don't need to do that. I can use impedance if what I say is I'm isolating myself to only consider cosines. The only downside to that is I don't get the transient response, right? But we always know that the transient response is equal to some sort of an exponential. If it's second order, it can be sort of an exponential and a sinusoidal sort of thing, but it's exponential nonetheless, right? It's just complex exponential. And the thing about transient response is it ends, right? It's transient. So it goes away pretty quickly, and then I'm left with the steady state most of the time. All right. So in that particular case, we say, you know, that sine waves are not the only type of special inputs that we could have, right? So the other thing, you know, I said, well, what if we had something like a square wave as the input? Well, you'd like to be able to use square waves and use the impedance idea. What I said was that if I had a square wave, I can think of it as basically an additive combination of cosines. And, you know, basically what that means is if I had a voltage source that looked like a square wave like this, I could replace that voltage source by a sum of sine waves, basically a bunch of individual voltage sources that were in series with each other. But that's not to say that that's what I really have. That's the important thing here is if I had a voltage source that was truly a square wave, which I could have, right? It's not really a bunch of cosine sources added in series, but I can make a model for it to say that it is. And that model makes my analysis a lot easier, okay? All right, that's the basic definition of a Fourier series. As long as I have a periodic waveform, then I can think of that periodic waveform as a linear combination of these sinusoids, what I call a periodic basis function. All right, so I call it a basis function because I can use it as the basis to build up a more complicated waveform, okay? And I said, you know, the example I use is solar. I used it before with you guys, but you know, you could think of this in context of robotics. All right, on the project, I'll do that. All right, where it's kind of in a robotic context, where what I have is a DC source, so a solar panel here on the left side. This guy is DC, but the grid is AC. And essentially, what I do is the waveform that comes out of the circuitry that I build is this sort of odd looking square wave. It's periodic. But if I understand what's going on here, it's just something called pulse width modulation. And if I knew the Fourier series for that odd looking square wave, then I could figure out how to drive this thing so that I connected to the grid properly over here. All right, so it's a useful analytical tool for us, this whole Fourier series concept. It helps us to do a lot of stuff from a design perspective that we couldn't normally do otherwise. All right, so there's three versions of the Fourier series is what we said. All right, they're all three of them are equivalent. So what I'm writing out here is they're all f of t as I've written it, okay? And this is true for any periodic waveform, meaning any wave for which f of t equals f of t plus a period. All right, that's their definition of a periodic waveform. And they can be represented in those three ways. The one that's probably most intuitive is probably this one, the first one, which is a combination of sines and cosines. The one that is the easiest to deal with mathematically is the one that is probably the strangest, which is the complex version of the series. Okay, so we're going to continue and focus more on that complex one here today, because that's the one that really ultimately becomes the, like I said, the most straightforward one to deal with from a computational perspective. All right, so what I showed at the very beginning was I said, well, if you got a square wave, then the square wave is the simplest thing to do. And I sort of said, if you added up sine waves, particularly sine waves, not cosine waves, but sine waves that had sort of these harmonically related frequencies. And what I sort of showed previously was I had something at the fundamental frequency. So in this case, the fundamental frequency is omega equal to 2 pi. And then I've got something that has 3 omega naught and 5 omega naught, so on and so forth. Then I could add those up in just the right way to fit into this thing if the amplitudes at the nth harmonic, right? So the nth harmonic meaning n times omega naught, right? At the nth harmonic had this 4 over n pi. Now the question is, where I started left off last time was, okay, well, how do I know that? Well, there's got to be a way to calculate that. All right, so that's what we're going to pick up with today, and this is what's in the current homework that's due on Friday, is starting to figure out those things. Okay. All right, so we had these core definitions. Basically, I said I got a fundamental period. It's the smallest period over which the waveform repeats, and then I can relate that to the fundamental frequency. And of course, there's an omega naught too, which is 2 pi times that. But this is always really what we tend to refer to as a frequency in hertz, right? Engineers don't typically refer to frequencies in radians per second. Just so happens that sine is defined that way. Okay. All right. Harmonic number n, and then harmonic frequency is n times that. And then we got to talk about this thing, the DC term, which we've talked about a couple of times now, but it's basically the average value of the waveform is the DC term. Okay. All right. So we're going to talk more about that again today. All right. So last week we said is if I had a Fourier series coefficient, there's two types of problems that we might encounter. There's the kind of contrived problems like you had at the very end of homework 6 and you have at the very beginning of homework 7, which is where I do something like this, all right, where I give you a function like this, all right, and I ask you by inspection to come up with what the coefficients are. That's one approach. That's not in practice the most useful. The other one, the more useful one in practice, is the second approach, which is where I got to solve for the coefficients. I can't just do it by inspection by looking at a particular waveform. All right. So if I've got a waveform that looks something like this right here, this is what you would come across in practice, right? I've got a particular measured waveform, in this case measured at the wall socket here in Epic, right? And I want to actually figure out what are the coefficients that would work. So we got to figure out how to do that, right? From the context of measured data. All right, so in the case of the inspection process, again, you got that at the beginning of homework 7 again. Basically, there's 3 steps to it. I find the fundamental period, I get the harmonic frequencies, and then I get the coefficients of those frequencies. Use in whatever form is the most natural, right? So when I look at this waveform, this is what we did last time. I look at this. This is where I look at that. And the sine cosine version of the series is the easiest one to look at. And then I got to find out ways to sort of shift between the different versions of the series. And so if I'm using that method, then what I do is what we did last time, right? I sit down and I go through this example of determining what all the different coefficients are. I've gone through this in detail now, where I figure out the A's and the B's, and then I take the A's and the B's and I convert them to C's and thetas, and then I convert those to alphas. Okay, and then, you know, in context of the way I ask you to put this in, it's just like this in MATLAB, where you fill in these vectors here. All right. What we got to do is move on to sort of the more general version of this, where I don't have a function that I'm giving. All right, the key thing is basically, like I said, section 9.1 in the book, all kinds of formulas that are there. We're not going to use most of those formulas. What I'm going to do is this is basically the set that you need. All right, the versions that are here are what you need. And then effectively what the thing we need to do is to figure out how to calculate the coefficients for those generalized versions of the series. All right, so the other item that we talked about last week is there's a special case, which is when I'm looking at the DC terms. Okay, the DC term is the average value of the waveform. All right, that is not in this sum, right? This guy is from n equal to 1, meaning that 1 times omega naught. The DC term is what number times omega naught? So what's the frequency of the DC term? 0. All right, the DC term has a 0 frequency. So that doesn't fit into this sum, nor does it fit into this sum. Okay. Now it does fit into this sum. All right. If you were to put in n equal to 0 here, you would get alpha n times e to the j 0, which would be what? Alpha n. All right. And I guess specifically because I'm doing it for n equal to 0, it would be alpha 0, right? Like that. Now, looking at this here, right? The thing that you see here is alpha 0 would be the DC term for the complex version of the series, whereas for the other two, it's A0 over 2 and C0 over 2. This confuses people a lot. Basically, what it means is if the DC value is, let's say the DC value is 10, that means that A0 and C0 would both be 20. All right, it's dumb, but it's the way that the book kind of defined it, and I'm just trying to be consistent with it. All right. So I ask for it that way, in the homework submission. Okay. All right. And there's never a B0. Okay, it's always equal to 0. All right, because you wouldn't need two versions of that. All right. So where we ended up last time was starting to calculate the arbitrary coefficients. Okay, so if I just have a waveform and I haven't given you a function for it, but I need to determine the coefficients. Now, one of the things I said, and we'll see this a little bit more carefully. If I ask you to do calculus with trig functions, all right, if you have some function times cosine or sine, that always becomes an integration by parts that you got to do twice. All right, it becomes messy. Exponentials, it becomes easier. So a lot of times it's easy for us to use the complex versions of stuff for a couple of different reasons, one of which is the calculus gets easier. All right. Another reason is that actually, like from a computer engineering perspective, it makes dealing with memory and things like that easier. All right. That's a little bit beyond us here in this class, right? But something like this is important for us to remember. So we're going to deal primarily with the complex exponential when we get these coefficients. All right. Now, like I said, normally I've got data like this. And so what I said last time is you can find formal derivations of how to solve for AN, BN, CN, and alpha N. All right. And I didn't want to do a formal derivation. It's time consuming and it's not necessarily the thing that's most useful for you. You guys care about what your grades are, not necessarily how to solve for that. You can read it if you really want to see it. Intuitively, it makes sense to me to try to figure out, okay, well, if I was given a waveform and I asked you to try to compute it, there is a way to kind of think it through. So if I gave you this waveform right here, all right, so 3 cosine 2 pi 1000 t. All right, we're actually going to do, we're going to do a couple of different waveforms here. I'm going to say this guy, and then 3 sine 2 pi 1000 t, and then 3 cosine 2 pi 2000 t, and try to figure out the coefficient, the first value a sub 1 in each of those series. Okay, so looking at this guy just by inspection, if I've told you the formula, what's A0, A1, B1, A2, and B2 for this waveform? What are they? if I gave you 3 cosine 2 pi 1000 t, does that have an A0 value? Does that have a DC?
No.
Yeah, no DC value for that, right? Does it have a B1 value?
No.
No, right? And then similarly, it doesn't have a second harmonic either, but it does have an A1, and that's 3, okay? Now, again, that's easy to do by inspection. What I was saying last time was I said, okay, if I took this picture right here, and I had a waveform 3 cosine 2 pi 1000 t, and what I did was I actually took that waveform and I multiplied it by cosine 2 pi 1000 t. All right, so I need a trig identity to figure out. So this is a block diagram. This is a very common thing that you're going to see in a lot of classes as you go forward. What I'm doing is I'm saying I'm going to take a waveform, multiply it. That's what this X in the circle means here. I'm going to multiply this waveform here by this waveform. And then what I'm going to do is I'm going to take the output of it. I'm going to average it over a period. And then I'm going to take the output of that. I'm going to multiply it by 2. Okay. So, all right. So I got 3 cosine 2 pi 1000 t times cosine 2 pi 1000 t. All right. That's a trig identity to simplify that. What does the simplification of that look like? If I had 3 cosine 2 pi 1000 t times cosine 2 pi 1000 t. What's that look like? I know, Logan, you know. Yeah. Yeah, 3/2 plus 3/2 cosine 2 pi 2000 t. Like that. If I multiply 2 cosines, I always get a term at the difference of the frequencies and the sum of the frequencies. In this case, the difference of the frequencies is 0. Now, again, I'm not expecting that you necessarily remember that trig identity, right? But that is the trig identity. All right. What I'm doing then is I'm saying I average that over a period. All right. So what did we say last time? What's the definition of an average of a waveform? The definition of an average, right, is I sum and I divide by the number of things I sum by, right? That's the way you think of an average. But averaging over a period, how do if I take a function and I average a function over a period, what is the formula for that? I told you I want to get the average of a function. What's the formula for that? Anybody remember? Yep. So yeah, t to t plus capital T, right? X of t dt, right? That is the definition of an average over a period. Okay. So, and technically it could be from t minus capital T to t. There's a couple of ways to write it, right? That's an average over a period. Now, if I look at this right here, if this was the waveform I had, 3/2 plus 3/2 cosine 2 pi 2000 t, I don't need to do any math on that. What's the average value of cosine over a period? 0, right? So the result here better be 3/2. All right. If I take 3/2 and multiply it by 2, it becomes 3. Right. That picture right there, if I looked at taking this, if I called this here x of t, right? If I called that x of t, I could take that picture and turn that into an equation. This equation this picture here would effectively be 2 over t times the integral x of t times cosine 2 pi f naught t dt. And I'm integrating from t to t plus t. That's what this whole picture here basically is, that equation. All right. Again, there's a way of taking of deriving that, okay, to show that that's how you figure out a sub 1. And I can generalize that to say, and the way I figure out a sub n is that it's 2 over t integral from t to t plus capital T of x of t cosine 2 pi n f naught t dt, like that.
Dr. Cox,
Yeah.
Could I ask where the 2 came from and the 2 over t?
So the 2 came from this step right here. The fact that after I averaged, I was left with 3 halves, and I know the coefficient here was 3. So in other words, at this step, once I've gotten to the 3 halves, what this process has determined is 1/2 of the actual coefficient. So I multiply it by 2 to get it to what the actual coefficient is.
Okay, gotcha. Thank you.
So it's really just a correction factor that's kind of thrown in there at the end to get to the right answer. So and basically what I can do is I can show pretty carefully if I took I guess I had a picture of it there, but if I took sine of 2 pi and I multiplied it by cosine, what I would find is that the result of that would have 0 average. And similarly, if I took the second harmonic and took it through this process, I would also get something that was 0. And that leads ultimately to the fact that the general formula for the A sub n and the B sub n are what I have right here. Okay. And this holds true. And again, here I did it from 0 to t. I guess in general, I really should say that it's from t to t plus capital T. All right. Because sometimes what we'll find is that it is advantageous to do it over a different period, although usually you're going to do it from 0 to capital T. All right. Sometimes for whatever reason, it makes the math easier to do it from maybe like a negative t over 2 to t over 2 or something like that. All right. But generally speaking, you do it over 0 to t. All right. Now, this only holds true for what values of n? What value of n does this not work for? 0. Okay. So this is true here for n greater than or equal to 1. Okay. Now, the other formula, again, without deriving it, the other formula that we have is that for the alpha values, it's 1 over t x of t e to the negative j n omega naught t dt. All right. And again, that applies from t to t plus capital T. If you want to, there's a whole mathematical derivation of that formula if you want it, all right, in the book. All right. Because technically, my hand wavy explanation of it, it works, right? And it actually, when I follow that, it makes intuitive sense. All right. But there is a whole derivation for how you come up with that. Okay. We're going to use this one primarily. All right. Once I have that, what I can do, all right, so there it is again, right? Once I have that version of the series, what I can do is I can relate between the alpha values to the C values, the theta values, the A values, the B values, and I can plot it however I want. Okay. All right. These ones, the math becomes really, the calculus gets really obnoxious usually when it's cosine and sine. It ends up being all kinds of integration by parts, whereas that's not usually the case when it's exponentials. All right. All right. So, and when you get into 3111 signals and systems, you're almost always going to use exponentials. All right. That's really the way that we tend to do it in all sorts of ECE stuff. Okay. All right. So back to a waveform. So let's apply this now. So if I've got a square wave here. So what I'm going to do is I want to apply this alpha n equation. So alpha n 1 over t to t plus capital T x of t e to the negative j n omega naught t dt. So I want to figure out the alpha n values from this. So what's my first step? How do I approach this now? Where do I start? Well, what's x of t?
Would you need to find the form of the Taylor series, or not Taylor, the Fourier series that you'd want to use?
Well, so I mean, I told you alpha n. I said it's going to be the complex version that I'm going to.
Okay, gotcha.
Okay. So that's set. Yeah. All right. So then basically what I'm saying is I'm going to plug it into this form. All right, so to do this, what are the first two things that I have to figure out to use that equation? I need to know which period I want to use. Yeah, and what else? Somebody's about to say something.
I was gonna say period and your frequency.
Well, yeah, so sure, I need to figure out the frequency. I need to figure out what period I'm going to integrate over. I also need a function x of t, right? So let's say that I'm going to do this over the interval from 0 to t. So I'm going to do it from here to here. All right, so I'm going to integrate over that period. So for now, I'm going to say I don't even care about a number. I'm just going to say omega naught is 2 pi over capital T, whatever that is. Okay. All right. So that's my waveform here. So what's x of t then? How would I define x of t over that period? Right here. So over the period from 0 to capital T, how would I define that? Well, yeah. So you guys are ready for a test tonight that's going to deal with things like you could call this, I don't know, P of t equal to U of t minus U of t minus t over 2. That would work. That's not really, that's ugly, right? So the other way I could define that is I could say that this is the number 2 for 0 to t over 2, like that. And then I could say it's 0 for t over 2 to t, like that, right? That's a simpler way to write that. That's the same thing as writing it in terms of the pulse function, like I did right there. But this would be a way that would allow me to easily do the calculus. Okay, so that turns this function here into 1 over t integral from, all right, so I'm saying I'm integrating over the first period. So from 0 to capital T of x of t. So, all right, so how do I do my x of t now? X of t is 2 for the first half of the period and 0 for the second half of the period. So how do I write my integrand there? Split it up. What was that? I cut somebody off.
Yeah, I was gonna say split it up.
Yeah, okay, split it up. So yeah, 0 to t over 2, right? And I say integrate 2e to the negative j n omega naught t dt. And then the other part of the quote splitting it up is 1 plus 1 over t over 2 to t of 0 times e to the negative j n omega naught t dt. All right, this guy, a definite integral of 0 is 0. All right, that part is going to integrate to nothing. All right, so what I'm left with is solving the first part of that integral. So my alpha n value now is 1 over t integral 0 to t over 2 times 2e to the negative j n omega naught t dt. All right, now that is ugly, but it's not hard. All right, if I look at that problem, it's basically like I have the integral of e to the at dt. What's that integral? E to the at dt. There's not many integrals that you should know in life, right? There really aren't. All right, but that's one that you probably should. What is e to the at?
1 over a e to the at.
Yep, 1 over a times e to the at. All right, so that tells me in this case, if I have alpha n is 1 over t, I'll pull the 2 out in front here, e to the negative j n omega naught t dt, and I'm integrating from 0 to t. All right, and one other fact that I'm going to keep with me is omega naught, we said, is 2 pi over t. Okay, so how do I use this fact here in this math? what do I bring down in front here? What does that become?
You pull down the negative j and omega naught.
Yep. So this becomes 2 over negative j n omega naught times t times e to the negative j n omega naught t. And because this is a definite integral, I say I evaluate that from 0 to t. Okay. All right. Now, the whole reason why I said this omega naught equals 2 pi over t is this guy's getting ugly. It's got lots of symbols, right? I got the whole Greek alphabet showing up here, right? So if I look at this thing, omega naught's 2 pi over t, I can say that this is 2 over negative j n omega naught was 2 pi over t. So I'm going to turn the omega naught into 2 pi over t times t. Okay. And then similarly here, I guess e to the negative j n omega naught t, I can do the same thing, n times 2 pi over t t and integrate from 0 to capital T. So if I have 2 pi over t times t, right, the t's go away. And I got 2 on top and a 2 on top, so they go away. So this guy becomes negative 1 over j n pi times, all right, so I got e to, so how do I evaluate this integral here? how do I do this part?
Substitute capital T for lowercase t, and then subtract that expression and plug in 0 for t.
Yeah, so this becomes e to the negative j n 2 pi over t times t. So that's plugging in capital T, and then minus e to the negative j 0, like that. Right, I'm not even going to bother writing in the rest of it because there's 0 in that one. So e to the j 0, what is that? It's 1, right? So this whole thing basically becomes over here, alpha n equals 1 over j n pi times 1 minus e to the negative j n pi. Okay. Yeah. J n 2 pi. Like that. Okay. Now, yeah, all right, that's right. Yes, we should have been integrating. Yes, thank you. 0 to t. So we said we broke this up into 2 integrals, right? So this guy was supposed to be from 0 to t over 2. I was having an extra. That should have been integrated to t over 2. So that turned this 2 here should go away because I actually put a t over 2 in there. All right, so this guy, after I go through the algebra, it becomes that. Now, that is not the most kind of intuitive thing in the world. All right, to look at that expression, okay, well, what the heck does that mean? All right. Now, one of the things that I said when I did the square wave at the very beginning, I showed you, right? I got the picture here, right? I said that only the odd harmonics were there. Now, again, this is looking at sines, but if I'm doing it with the complex version of the series, but it better be the case that there's no even harmonics present here. In other words, this guy shouldn't have anything for n equal to 2, which means that the even harmonics don't fit into the waveform. In other words, I don't need any number of even harmonics to give me that square wave. So how could I check that? Well, let's plug in n equal to 2. And then n equal to 4, and so on and so forth. So I think about this: 1 minus e to the negative j n pi. All right, so e to the negative j n pi, I can expand that, can I? What do we know about e to the j theta? What's that equal to, e to the j theta? What's that supposed to be equal to?
Cosine of theta plus j sine theta.
Yeah, cosine of theta plus j sine of theta. All right, so if I look at this, I can expand this into 1 minus cosine n pi, and a negative angle, cosine of a negative angle is the same as the cosine of the positive angle. All right, and I would get plus j sine n pi, like that. All right, so if I just a real quick, if I look at this here, what happens if n is any even number? What's that? Yeah, the sine term, this kind would go away, right? And if I plugged in n equal to, let's say n equal to 2, right? What's cosine of 2 pi? It's 1. So I'd have 1 minus 1. What happens if it was 4 pi? What's the cosine of 4 pi? 1. Cosine of 6 pi. So basically this term right here would become 0 for n even. All right. Now, that's me applying some logic to this thing, right? Logic that I'm not asking you to necessarily apply, right? In the homework, right? I'm basically just asking you to get me to this alpha n value, not asking you to simplify it. One of the questions you're going to ask me about probably a lot as you get to the next exam is going to be, well, how much do I have to simplify it? I'm not asking you to simplify it, right? That's an algebra trick to get this guy a little bit further simplified. Unless I explicitly tell you to do that, I'm not going to tell you to do that. Once I have this alpha n value, right, at that point, once I have the alpha n value, then, all right, I can use that to sketch the series. All right, and so in MATLAB, you guys are going to use this to sketch the series. All right, so what about if n equals to 0? Because this is what's going to cause you guys problems when you start writing your code. You're going to write code, and we're going to talk about how to write some of the code here in a second. But what happens if I plug in n equal to 0 into this expression? Yeah, this guy's going to become infinite, right? If n is equal to 0, this guy is technically undefined. So that's going to cause you a problem, because if I looked at this, it's supposed to be the average value of this particular waveform, right? If I looked at this, the n equal to 0 term is actually the average value. So just by inspection, if this was my waveform, what should alpha 0 be if this is my waveform? Not infinite, right? If I plugged in n equal to 0 into this waveform, there's an n in the denominator, right? That's going to make it infinite, but that's sure as heck not what it is. All right, so what is it actually? Just by inspection, looking at that waveform, what should it be? 1. The average value of that waveform is 1. So alpha 0 is really equal to 1. So I got to approach the DC term separately. I said it's the average value of the waveform, which we've already said is, so alpha 0 is 1 over t integral 0 to t x of t dt, like that. It's that value. Now for this particular waveform, that's super easy to do. All right. Basically what that's saying is that alpha 0 is 1 over t integral 0 to t 2 dt. All right. I could go through this and I could do some math on this. So I would get, what's the integral of 2? Why did that turn off? What's the integral of 2? Be 2, yeah, well, in this case, 2t, right? But it's actually even easier than that, right? If I think about what is it, this is an area, right? So it's basically the area under this box, right? So this would actually work out to be 1 over t times 2 times t over 2, right? Basically the height times the width, like that, right? So if I know intuitively what an integral is an area under the curve, this guy clearly works out to be 1. All right, now the thing, so in this particular case, my alpha 0 is 1. All right, so in general, this is the thing I mentioned already, right? So usually if you're trying to figure out this n equals 0 term, we use the average equation. So basically we use this equation here. All right. So alpha 0 is the average over a period. Again, typically we look at the average value over the period from 0 to t, but in general, it can be any period. All right. So this would be of x of t. I guess to be consistent with what I've got here on the slide, I'll say f of t dt. Okay. All right. Looking at this, then I can relate them as shown below here. So A0 and C0, it's always going to be the case that A0 and C0 are twice what the actual DC value is. All right, just because of the way that the series are defined. All right, not my choice. That the world defined that a long time ago. All right, that's going to cause a bunch of you to lose points on the exam probably, right? Is you'll forget that point. Okay. All right. So DC term always gets treated differently. And I say this because in code, if you're writing a for loop or something like that, all right, the thing to bear in mind is if you're looking at something like this alpha n value, if you plug in n equal to 0, you're going to get an infinite value. So you got to be careful about that. So, all right. So what the kind of thing that I would ask you to do, all right, would be to say, and you have this, I don't know what problem it is, but you have a couple of problems like this on the current homework, all right, where I ask you to figure out the alpha values and then to write a piece of code that will generate a plot of the function. Okay. So you got a couple of problems like that on the homework. So how would you approach that type of thing? So what I have here is, so here's my alpha n value for that square wave. All right. So in this particular case, I said my F naught was 1 kilohertz. All right, so there's my F like that. I defined my omega naught and everything. I defined a time vector. And what I've done down here is I have a section here where I build the coefficient vectors, I'm saying. All right, so there's where I build up the alpha vector. So when I say the coefficients, what I mean is the alphas. So I'm going to build up the alphas. Now notice because I'm doing alphas, I got to do this from whatever the largest coefficient is, the negative of the largest, to the positive of the largest. So in this case, I've said the maximum. So technically, it takes infinitely many harmonics to do this, right? So when I did this, so it really I should have looking at the formula for the series. Where's the series? All harmonics can be used. Okay. The thing is, if I asked MATLAB to make a graph for me that had infinitely many harmonics in it, the loop would never finish, right? But in general, I don't need to have, usually as the n value gets larger, as they get to higher and higher harmonics, usually they have less of an effect on actually sketching the waveform. That's maybe an important point. If I looked at this waveform right here, I know for a fact that this waveform, which I measure here at the wall outlet, it's got a fundamental term and a third harmonic and a fifth harmonic and a seventh harmonic and a ninth. But by the time I get to like the 21st or the 23rd, 25th, those harmonics are starting to get awfully small by that point. All right. Usually that's the case, right? Like when I drew this square wave here, all right, this guy is using the 90 up to the 99th harmonic. That's pretty high. Now, square waves have this interesting effect where they kind of grow ears like this. All right, and that's a mathematical sort of effect of trying to plot a Fourier series, something called a Gibbs phenomenon, which we could talk about, but it's not that particularly important. All right, only to the extent that I started putting in infinite numbers of harmonics would those ears go away. All right, so that's a phenomenon that happens in real life. Well, let me put this, you don't see that in real life when I try to put a waveform together, but this is a mathematical artifact that sort of occurs. Forget about that. If those ears weren't there, what you would see basically is that's starting to look a heck of a lot like a square wave. Okay. All right. And I think if you read in section or in chapter 9 of the book, I think it'll talk a little bit about that Gibbs phenomenon thing where it starts to add those ears in. Okay. All right. So back to my code here. Right. So what I did was I'm creating an alpha n vector. So notice what I did was I created an empty vector. Okay. Now in my example, I did n equal to 2. So very, very simple. This will go to the second harmonic. Now, because I'm doing the complex version of the series, that's going from -2 to 2. Okay. So what I do is I write a for loop that loops through from 1 to the length of that complex vector. And notice what I'm doing in each of, so I've got an if statement in here. Why do I have if n complex of k is equal to 0? What is that if statement there doing? Why did I put that there?
Is that your DC term?
That's my DC term. If n is equal to 0, so my n complex basically is the harmonic number. So these are the harmonic numbers. So when n equals 0, that's the DC term. So notice how I'm building up the alpha n vector. What is this kind of notation that I've got? Alpha, I have in square brackets alpha n followed by the number 1. Well, the number 1 is the DC value. All right. So what is this doing here? Any ideas? I'm saying alpha n equals in square brackets alpha n plus the value alpha 0. So alpha 0 is the last entry. Alpha 0 is equal to 1. What am I doing? Yeah, this is a concatenation is what this is, right? Basically what I'm doing is I'm saying the alpha n vector should be equal to whatever the alpha n vector currently is, plus the next entry I want to add to it. Okay, so maybe I should start with the else statement here. With the else statement, this is basically for n not equal to 0, where I'm using this formula right here, right? So notice what I have. I have right here, I'm saying whatever my existing alpha n vector is, and tack on to it 1 over j pi times my value of n. That's what this n complex of k is, times 1 minus exponential of minus j times whatever value of n I have right now, times pi, right? That's basically me putting in that formula right there. All right. And what's going on here is a concatenation. I'm basically at this point, I'm saying my alpha n vector is equal to whatever my alpha n vector currently is. And then I'm putting in there the formula that I derived for alpha n. Right. So this guy is alpha n equal to 1 over j n pi times 1 minus e to the negative j n pi. Like that. All right. So it's a concatenation is what that is. It's the easy way to concatenate. All right. One other way you could do this the code is one of those things you can write as many different ways as you want, right? So I could have probably said that the alpha n vector was equal to zeros with the size of n complex. All right. That would be another way to do it. All right. But this is how I'm doing it here. I'm just concatenating them. Okay. Now, what I then do at the end of this is if I want to make a plot of the function, and that's the thing I also ask you to do in the homework is to make a plot of it. Now, I'm not plotting the actual function. What I'm doing is I'm plotting an approximation to the function because there is no way on earth that I could plot f of t for n equal negative infinity to positive infinity. Not possible. All right. So what I'm doing is I'm saying, all right, my function, which I'm calling x, I make a function x that's equal to zeros with size of t. All right, so t is my time vector. So what I'm doing here is I'm creating a vector that's going to hold x of t. All right, so I got a row vector that's going to hold x of t. Now, what's going on in my for loop here? So for k equal 1 in steps of 1 up to the length of n complex, what am I doing here? Forget the if piece. Let's jump to the else first. What am I doing? I'm saying x equals x plus alpha n of k times this whole expression. What am I doing here in this line? Because this is probably the most important line of the whole code here. What am I doing? Well, I'm mathematically writing out this function right here. I'm basically saying take whatever I already have for x and add to it whatever the next value is from this series. So I'm basically saying, so basically it's to say, instead of x of t here, I'm saying x of t is equal to whatever x of t already is, plus alpha n e to the j n omega naught t. And I'm looping through my n values. So that's going to build up this thing, right? So if you think about what this summation means, every time I run through this summation for a new value of n, I'm adding in alpha of n e to the j n omega naught t. I do that for n equal to 1, and then for n equal to 2, and then for n equal to 3. And every time I go through that, I add on to whatever I already have. All right, that's what this expression here is doing. And if I execute this code here, all right, I added a function here called square. All right, so that's a MATLAB function that will generate for me a square wave. And I'll see that they look similar, right? So what I called x, which was my approximation to the square wave, my approximation and the actual square wave will look pretty similar. Now, because the square wave has this whole Gibbs phenomenon thing, I said, right, I'm going to get these ears. Where is it? I'm going to get these ears again. For a lot of other functions, that doesn't happen. All right, and they start to look pretty darn close. All right, but the square wave has this weird ear thing that it develops. All right, so that's a big part of what I'll ask you to do is basically I'll be asking you to figure out these alpha values and then to write the code to actually kind of generate this sort of a graph. Okay. All right, so this code is pretty similar to what you would do, but hopefully the process that I'm following kind of makes some sense. Yeah, Miles, is that Miles?
Yeah.
All right.
So for this x, we're doing x plus alpha and all that. What's when we're for the alpha values? Are you want to do the exact same thing different syntax or?
Yeah, so okay, so his question's about, yeah, I think the difference between these two things. Basically, I've got two separate loops. I probably could put them into one loop, I guess, if I wanted to. What I'm doing is I have one loop where I calculate the alpha values for all the values of n. And then my second loop is creating the x values for all of the values of n. Technically, those could be in the same loop.
I think it's confusing. Can you explain what the brackets do? Like it's a bracket alpha of 1.
Yeah, so when I do this whole thing where I say alpha n equals square brackets alpha n and then a number, and technically, this doesn't look like a number, but it's a number, right? Once you evaluate 1 over j times pi, that's going to be a number. If I have alpha n equals alpha n and a number, then I just add that number on at the end. So here, let me.
Oh, okay, so you just add it to the end of
Yeah, so let me do it this way. I'm adding in, so if I use the term concatenation, does that make sense?
yeah,
What's that?
I know that.
Okay, yeah, I never. So let's take an example. So alpha n, so I started out with it when I initialized it, I said alpha n is equal to that. So it's nothing at that point, it's empty vector. So if I have a for loop, so for n equal n equal 1 to 1 to 10, let's say. If I did alpha n is equal to alpha n, I keep wanting to write that. And let's say I put the number n like that. Okay. What this would do is the first, so for n equal 1, I would end up with alpha n equal to 1, like that. For any after n equal 2, it would be alpha n 1, 2, and then it would just so on and so forth. And actually, if you take a piece of code like this and you don't put semicolons after it in MATLAB, you can actually watch that, right? Where it would build up that way. You would see it be 1, 2, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and it would write that out at the screen for you. As long as you got a manageable number like this, that's actually useful to see in MATLAB. Don't put in up to 10,000 or something like that. You'll be sitting there for a while. All right, but this is a way to concatenate vectors, basically. I'm adding a number on to the end of it. All right, other questions? All right. Yeah. All right, it's a good question. All right, so then the inevitable thing that I also ask you is, all right, well, then give me the other versions of the series. So we figured out how to do the alphas. There is a formula which I already gave, right? There is a formula. I went past it. Okay, for the A's and the B's. There's one for the C's and for the thetas. Right? I don't even know what it is for the C's and the thetas exactly. It's ugly. But what we do is once you know the alpha values, it's really easy to go back and forth between the different forms of the series using the formulas that we already kind of derived. I said there's 4 ways of representing a sine wave, okay, at any given frequency. There's 4 ways of doing it. One of them is this sort of the most intuitive way of saying what's a cosine at any given frequency is this basically cosine of omega t plus a phase shift. All right, that's kind of the most intuitive way of doing it, because you say in general anything can be represented by a phase shift away from whatever a basic cosine should look like. The second way of doing this is to say that this function x of t that I wrote here could be written as a cosine plus a sine. But notice there's never any phase shifts in either of these. Right, so it's a cosine and a sine at the same frequency. Cosine and sine, what's the phase shift between those two? 90 degrees. Maybe it's negative 90 degrees. I don't know. They're 90 degrees apart from each other, right? And what we're saying is any cosine at a given frequency can be written as a sum of sine and cosine. Or I can think of that whole thing as this sort of 2 rotating vectors, one going in the positive direction, one in the negative direction. Or I can think of it as the real part of some vector that's always moving in the positive direction. All 4 of those things are entirely equivalent. And I can use these relationships here to get between them. Okay. So there's no sense in calculating. If I can get the alpha values by calculus, then it's just a matter of plugging into these formulas here to get the other ones, right? And that's basically what I'll ask you to do. So let's say that I asked you to do that. So let's say I had, the square wave, and I calculated the alpha values that I did, right? So I had the alpha n equal to 1 over j n pi times 1 minus e to negative j n pi. So I had that whole thing there. And I said, all right, well, what I want to get from you is not just the alpha n values, but I want to get the an, I want to get the bn, I get the cn, I want to get the theta n. And then I want you to plot all 3 versions of those. So in other words, when I say plot, I want you to show me x of t from the complex, x of t from the sine cosine, x of t from the shifted cosine. So basically, I got to go through the whole process again. All right, so this is the way I would code that. So in this case, I'm plotting up to the 9th harmonic. Okay, so I created a vector here that goes from -9 to 9. All right, because the complex version of the series, I have to have two rotating vectors, one in the positive direction, one in the negative direction. And it's the same for loop to calculate my alpha values. Once I have that, notice what I have inside these loops that I added, right? I added for myself here inside this for loop, where I'm calculating my C sub n values. So let's focus on the else statement here. I'm calculating my C sub n, my theta sub n, my A sub n, and my B sub n. Okay, so forget about everything else there in the code. Let's just focus on this part in this else statement. So what I'm doing is I've created an n vector which goes from 0 to n, or 0 to capital N. So just to be clear, capital N here, this is the highest harmonic of interest, let's call it. So in other words, I'm only trying to go up to the nth harmonic. Technically, n goes to infinity, but I'm saying let's just go to the ninth. All right. What I created was this n complex value. All right, so n complex went from -9 to 9, and I calculated the alphas. All right, so this guy is going to have, if I go through the math here, I think it's going to have 19 values of alpha n. That's going to go from -9 to +9. Okay. So what I'm saying here is, all right, well, what I want to do is I want to also calculate the AN, BN, and CN, and theta n. So I basically loop through and I create a new vector n, which goes from 0 to capital N. So this is going to go, this vector would be from 0 to 9 as I've defined it, right? Because capital N is equal to 9. So notice what I'm doing here in this else statement. Now let's focus in on the else statement. So what have I done? I've said C of n is equal to whatever my C of n vector already has. And then I added to that abs of alpha positive of k times 2. All right, so well, what am I doing there? I'm taking the magnitude of the alpha value times 2. Well, where did that come from? Well, right here, right? The magnitude of alpha is equal to C sub n over 2, using the formulas that we've got there. Remember, it's always the case that this guy is C over 2 times e to the j theta n, e to the j n omega naught t, plus basically the conjugate of this times e to the negative j n omega naught t equals that whole function. So what I've done here is I'm basically implementing those formulas here in my code. So I'm taking the absolute value, which is the magnitude of it, times 2. So my theta value here, notice what I did was I took the angle of it. Okay. So for my A and B values, what I did was I went to the formulas here and I basically said, well, it's C times cosine theta. And for B, it's negative C times sine theta. All right. Now, the thing that's maybe a little confusing, I said alpha positive. All right. Why? What am I doing here? Alpha positive. What do you think I'm doing there?
There's half as many values in the other forms.
Yeah, that's right. Yeah, basically, there's a whole set of values for the n equal negative numbers that I don't need when I'm calculating my A's, B's, and C's. So I'm basically throwing those away. All right. Now, what's this if k equals 1 thing going on here? Well, if k equals 1, that's going to be giving me n equal to 0. What frequency when n equals 0? So that's 0 times f naught. What frequency is that again? What frequency do when n equals 0, what frequency do I have?
There's no frequency.
0, that's right. DC, right? DC, 0 frequency. And so what I'm putting in there, notice, is 2 times the value of alpha, 0 into the B series, 2 times the value of alpha, right? And then for the theta, I gave it an angle. Okay. Remember back to my relationships there for the DC terms, right? I always said that my average value is whatever alpha naught is. And then A0 over 2, C0 over 2 are equal to that, right? So that's why I have my alpha 0 value, right? My alpha's 2 times my alpha value, right, is what I have right there. Okay. Now, what's this thing with the angle? Right? If you look at this here, A0 over 2, the average value of a waveform, is that ever going to be a complex number? Well, technically all numbers are complex, so yes. All right, but is it ever going to be imaginary? No. But what could it be? Like I could have a square wave that looked like this, right? It could be, but that's totally valid, right? Where this is -2. The average value of this would be alpha 0 equal to -1. That's the average value of that waveform. -1, how do I write that as a complex number? Yep, that is e to the negative j 180 or 180. Technically, it's either one. All right. So the number -1 is e to the j 180. Technically, that is actually Euler's identity. The fact that -1 equals in radians e to the j pi. All right. One of the things that people find to be it's a weird, mysterious formula. -1 equals e to the j. All the weirdest numbers in math basically are there in that one equation. All right. So if I look at this -1 equals e to the j 180 degrees. You got to remember the DC term could have an angle of 0 or could have an angle of 180. All right, that's the thing you got to be careful about. Just because that DC term is always a constant real number doesn't mean it doesn't have an angle. Its angle could be 180. All right, that's something to bear in mind. If it's a negative number has an angle that's 180 degrees, even though it's real. Okay, so a lot of what you guys have on the homework this time is really going through and writing code like this. All right, so what I did again here is I went through and I basically said, okay, what I would typically do is I would get the alphas first, use the alphas to get the A, B, C, and theta. And then what I have going on here is I wrote code to generate what the function should look like. So here's me creating the function using the alpha values, the complex form of the series. And then down here, I have another version of it doing it for the A version, the AB version of the series, and for the C theta version of the series. Okay. Now notice the thing that I did differently is in both cases, both for the complex and for the other versions of the series, notice what I did here. Again, I checked to see if n equals 0. Now, what am I doing in the n equals 0 thing? Well, that's the DC term. So I'm basically saying it's, x equals x plus, what am I doing here? What is that statement there doing?
Is this where you're concatenating all your DC terms?
Well, so I only have one DC term, but I'm multiplying it by the vector of ones. The vector of ones is basically just all ones. So I'm basically multiplying the number 1 by whatever the value of alpha is to add a DC term. So this is adding many, many terms to x that all have the same magnitude, right? So that's effectively what I'm doing there. All right, we'll talk about that real quick there at the beginning of the lecture on Wednesday as well. All right, and we'll wrap up on this. All right, so